Hi, I'm SeungHoan from Nagoya University, and it is a joint work with Masahito Hayashi from Southern University of Science and Technology. The title of this talk is Quantum Private Information Retrieval for Quantum Messages. So in this talk, we consider the quantum version of the problem called private information retrieval. So at first, I want to introduce what is this problem, and next, I'll explain the existing results of the quantum private information retrieval, which only treated the classical messages. And thirdly, I want to explain our result on quantum messages. So let me start from the private information retrieval, which I call PIR in short. So PIR is a retrieval protocol without revealing which message is requested. So it can be easily understood by comparing with the usual retrieval scenario. So in this figure, the server has F files M1 to MF, and the user want to know MK. And for that, the user sends K and receives MK, so the user knows what is MK. But the server also knows what is the case. The user's information is leaked. So in PIR, we want to keep this K secret from the server. So for that, the user sends a query and receives answer and may repeat this process multiple times. And finally, the user knows MK, but the server shouldn't know what is the K. At first glance, it seems very difficult to find the solution of this problem, but there is a very simple solution of just downloading all files in the server. By downloading all files, the user knows MK. User pick the MK from this, but the server doesn't know which one is exactly the targeted one. However, this solution is very inefficient, and unfortunately, it is proof that this downloading all solution is optimal. So this problem has been studied by two approaches. The first one is the PIR with computational assumption, and the second one is PIR with multiple non-communicating servers. And I want to move on to the quantum case, the quantum private information retrieval for classical messages. So as in this figure, the model has been changed as the channels are quantum channels, but the messages are classical. And on this problem, as far as we know, all existing studies consider the quantum private information retrieval for classical messages. And one interesting result for this approach is on the single server case, there exist efficient QPR protocols, which means that there exist QPR protocols cost less than downloading all solution. However, if we consider a little bit more stronger server model called the specious server, which assumes that the server may deviate from the protocol, but the malicious operations should not be noticed by the user. But in that case, the results became negative. So in our study for quantum messages, we want to know if this downloading all is still optimal or not. So I move on to our result. So we studied the QPR for the quantum messages. So the server contains the states. And the server's containment of the states can be considered by two settings, blind and visible settings, which are often studied in the state compression. In the blind setting, the server contains the quantum systems with determined states. In the visible setting, the server contains the description of the states. So, and our results are these three results. So one is positive result, and the two are, one is negative result, and two are positive result. So as our first result is that downloading all is optimal for one server QPIR. And our second result is that there exists an efficient one server QPR protocol with shared entanglement. And the third result is that there exists efficient two server quantum symmetric PIR protocols on the visible setting. Here, symmetric PIR means that the user only obtains the row K, but no other information of the other states. Thank you for listening.